In the oldest light in the universe, there is a wound, a place where the temperature drops in a way that has no business existing, a cold patch stretched across almost 2 billion light years of sky, sitting there in silence since the beginning of time. Scientists call it the cosmic cold spot, and this single anomaly has forced some of the world's greatest physicists to consider a possibility so strange, so enormous, that even saying it out loud feels like stepping off the edge of reality. What if that cold patch is the bruise left behind by a collision with another universe? What if our universe is not alone? Today, we are going inside that question. We are going to understand what the cosmic cold spot actually is, how it was found, what science says about it, and why some researchers believe it might be the first real evidence that parallel universes are not just science fiction, but science fact. To understand the cold spot, you first need to understand what it lives inside. About 13.8 billion years ago, the universe began with the Big Bang. Everything that exists, all matter, all energy, all space itself, exploded outward from a single point of infinite density. In those first moments, the universe was unimaginably hot and dense, a blazing, churning soup of particles and radiation so tightly packed that light could not even travel freely through it. The universe was opaque. Then, about 380,000 years after the Big Bang, something changed. The universe had cooled just enough for electrons to settle around protons and form the first hydrogen atoms. And the moment that happened, light was suddenly free. It could travel, it could move, and it has been moving ever since. That ancient light, that very first flash of freedom that raced across the early universe, is still out there. As the universe expanded and cooled over billions of years, that light stretched and faded. Its wavelengths grew longer. What was once a blinding glow became a whisper. Today, it exists as microwave radiation, filling every corner of the cosmos equally, in every direction, a faint, cold echo of the universe's fiery birth. This is what scientists call the cosmic microwave background, the CMB. It is the oldest light we can ever observe, a photograph of the universe when it was just a few 100,000 years old. In 1964, two American radio astronomers named Arno Penzias and Robert Wilson were working with a large antenna in New Jersey when they detected a persistent background noise they could not explain. No matter where they pointed the antenna, the hiss was there. They even cleaned out pigeons that had nested inside the equipment, thinking the birds were causing interference. The noise remained. It was everywhere. It was the CMB, the cosmic background radiation of the entire universe, arriving at their antenna from all directions simultaneously. They had accidentally discovered the echo of creation. For this, they won the Nobel Prize. Now, the CMB is not perfectly uniform. Across the entire sky, there are tiny temperature variations, fluctuations of just millionths of a degree. In the early 2000s, NASA launched a satellite called the Wilkinson Microwave Anisotropy Probe, or WMAP. Its mission was to map the entire CMB sky with unprecedented precision. For years, it stared into the cosmos, collecting data, building the most detailed picture ever made of the universe's earliest light. When scientists analyzed that map, most of what they found matched the predictions of cosmology beautifully. The CMB was almost perfectly smooth, with the expected tiny variations sprinkled across it randomly. Almost. In 2004, a team of astronomers noticed something odd in the direction of the constellation Eridanus, the river, in the southern sky. There was a region where the CMB temperature was colder than it should be. Not slightly colder, significantly colder. The spot was about 70 microkelvin below the average temperature of the surrounding CMB. That might sound trivially small, but in the world of CMB physics, where every deviation tells a story, this was enormous. Statistically, the probability of such a cold region appearing by random chance is less than 1 in 1,000. When cosmologists put that into the language of statistical significance, they called it a roughly 3.3 sigma anomaly, which means it is real enough that dismissing it as a fluke requires a very strong argument. And then there was the size. The cosmic cold spot spans approximately 1.8 billion light-years across. To put that into perspective, the entire Milky Way galaxy is only about 100,000 light-years wide. This thing is roughly 18,000 times larger. It is not a small blemish. It is a continent-sized scar on the face of the oldest light in existence. In 2013, the European Space Agency's Planck satellite, which had even higher resolution than WMAP, re-examined the same region of sky. The cold spot was confirmed. It was not an instrument error. It was not a data processing artifact. It was real, it was cold, and no one could explain it.
Once the cold spot was confirmed, the scientific community got to work trying to explain it. Several hypotheses have been put forward, and each one is fascinating in its own right. The first and most widely discussed mainstream explanation is the supervoid hypothesis. In 2015, a team from Durham University in England discovered that in the direction of the cold spot, there appears to be a vast region of space that is almost entirely empty. A supervoid. An enormous bubble of nothingness, roughly 1.8 billion light-years across, containing far fewer galaxies than you would typically expect. The idea is that as CMB photons travel through this void, they lose a small amount of energy through a mechanism called the integrated Sachs-Wolf effect. When light falls into a gravitational well and then climbs back out, if the universe is expanding and the well has changed during that time, the light ends up slightly colder than when it entered. A supervoid of sufficient size and emptiness could, in theory, produce a cold imprint on the CMB. But here is the problem. When scientists ran the numbers, they found that the supervoid they discovered is real, but it is not nearly empty enough or large enough to fully account for the temperature difference seen in the cold spot. The void can explain maybe a fifth of the anomaly. The rest is still unexplained. The second explanation is something called a topological defect, specifically a texture. During the period of cosmic inflation, the incredibly rapid expansion of the universe in its first tiny fraction of a second, quantum fields may have developed large-scale structural imperfections, similar to cracks or wrinkles that form when a material cools unevenly. A cosmic texture is a kind of knot or defect in the fabric of a quantum field, and if one existed in the early universe, it could have left a cold imprint in the CMB as it unwound over billions of years. This is a theoretically possible explanation, but it remains highly speculative and has not been confirmed by any direct evidence. The third explanation is the one that many scientists reluctantly mention but cannot quite rule out. Now we reach the idea that has captured the imagination of physicists and the public alike. The idea that the cosmic cold spot might be a scar left behind by a collision between our universe and a parallel one. To understand this, you need to know about the multiverse. Modern cosmological theory, particularly the theory of eternal inflation, suggests that the Big Bang was not a one-time event unique to our universe. During the inflationary period, the exponential expansion of space in the universe's very first moments, quantum fluctuations in the inflaton field could have caused different regions of space to stop inflating at different times. Each region that stopped inflating would then evolve into its own universe, with its own physical laws, its own constants, its own history. These individual universes are often called bubble universes, because in the mathematics of eternal inflation, they form like bubbles in a foam of still inflating space. Our universe is one bubble, and there could be infinitely many others, each completely separate, each inaccessible, each unknowable in ordinary circumstances. But here is where it gets extraordinary. If bubble universes are distributed throughout a larger inflationary space, and if they are expanding, some of them may eventually collide. Two bubble universes traveling through the inflationary background could slam into each other. And when they do, the collision would not destroy everything. It would leave a mark. It would leave an imprint on the CMB of whichever bubble survived, a circular region with a distinct temperature profile, colder or hotter than the surrounding sky, with clean, smooth edges and a specific geometric shape. In 2015, physicist Stephen Feeney and his collaborators published a paper in which they searched the CMB for exactly this kind of signature. They were looking for the telltale circular bruise that a bubble collision would produce, and they found that the cosmic cold spot is a candidate.
Its size, its shape, its temperature profile, and its location in the sky are all consistent with what the mathematics of a bubble universe collision predicts. This does not mean it is a collision. The supervoid explanation is still possible. A statistical fluke is still possible. But what it means is that the cold spot has not yet been explained by anything we know for certain, and the most exotic explanation on the table, that another universe once bumped into ours, has not been ruled out. Think about that carefully. We are not talking about science fiction. We are talking about a peer-reviewed, mathematically serious hypothesis written by physicists at major research institutions that our universe may have physically touched another universe, and that we are looking at the bruise right now, embedded in the oldest light that exists, waiting in the southern sky.
The cosmic cold spot remains unsolved. As of today, no single explanation has won the argument. The supervoid is real, but insufficient. The topological defect is possible, but unproven. The statistical fluke is allowed by mathematics, but rejected by intuition. And the bubble universe collision is consistent with the data, but unconfirmed by anything beyond it. This is what the frontier of science actually looks like. Not textbook certainty, not clean diagrams with arrows pointing to definitive answers. The frontier is a cold patch of sky, 1.8 billion light years wide, that refuses to behave the way our best models say it should. And that refusal is not a failure of science. It is an invitation. Every time something in the universe does not match our expectations, it means our understanding is incomplete. It means reality is larger than our current map of it. The cosmic cold spot could be the edge of that map, the place where our knowledge stops and something genuinely new begins. Whether it is a void, a defect, a coincidence, or a scar from another universe pressing against ours in some unimaginable cosmic collision, what it tells us is the same. We are small. The universe is vast beyond any scale our minds were built to comprehend. And somewhere in that vastness, in the cold, dark silence between the galaxies, there may be answers to questions we have not yet learned how to ask. If you made it this far, thank you for watching. Drop a comment below and tell me what you think. Is the parallel universe hypothesis science or science fiction? Where do you think the line is? Subscribe if you want more videos like this, and I will see you next time.